AP Calc BC, Unit 5, Day 10, Office Hours. So this was Trig Substitution. These were out of your book from Calc AB, the white book, page 547, problems 1, 3, 4, 7, 9, 11, 19. Should check the odds in the back of the book or the file that I uploaded that had that picture of that page. There's one even problem, so I guess I'll I mean, yeah, we'll do the even problem. But I'll just do them in order. Number one was the integral of square root of 4 minus x squared dx. If you tried to use substitution, it would not work. Okay, so can't do use substitution. So we're going to use these at least once on your homework. Be able to write these: sine squared plus cosine squared equals 1. You divide everything by cosine, that would give you tangent squared plus 1 equals secant squared. You divide everything in the first one by sine, and give you 1 plus cotangent squared equals cosecant squared. And there's some other versions of these, like, we could say that, sine squared equals 1 minus cosine squared, or the other way around. You could use that one. We could say tangent squared equals secant squared minus 1. I'm probably going to use this, or this to make one of those patterns happen. You could use all of them. There's 6 possibilities. Now, this is going to be where the 1 ends up. So that's going to be like our A value. And so we need to pick X. We need it to have a 4 in it, so we're going to put a 2 in there. And it's got to be a 1 minus a number. So I think we're going for this one, cosine theta. So then dx is negative 2 sine theta d theta. And so then we would rewrite this as the integral of 4 minus 4 cosine squared theta. And then dx is going to get replaced by negative 2 sine theta d theta. We can take the square root of 4 out. We could put this negative 2 out in front. Square root of 4 comes out. 1 minus cosine squared theta. And we still have a sine theta d theta. Now, 1 minus cosine squared is sine squared. This is what we're trying to force to happen. And the square root of sine squared is sine. So then we get negative 4 sine squared d theta. So now we're ready to integrate. But we got to use that double angle identity that we use all over the place in polar to integrate polar. So it's going to be 1/2 minus 1/2 cosine double angle 2 theta d theta. We could bring the 4 back in. So when you integrate this, is going to be negative 2 theta. Okay, so that's going to be positive plus, now it'd be sine 2 theta, but then you're going to get extra 2 popping out, so you got to divide by 2 because the chain will, and then it's going to be plus c. So this is what we have so far. Now we got to put it back into x, and so we're going to use this up here, and I'll probably draw a little picture. I'm going to say, well, cosine theta equals x over 2, which is adjacent over hypotenuse. I can draw a little triangle here, adjacent over hypotenuse. So this is going to be 4 minus x squared, square root of 4 minus x squared. But we have sine of 2 theta. So how do we deal with that? Well, we have to use a double angle identity for sine, which I wrote in the notes yesterday. And what it is it ends up as 2 sine theta cosine theta. That's the double angle. That's what sine 2 theta equals. So you got to do that first. And then, now theta itself is going to be inverse cosine of x over 2, right? Theta equals inverse cosine of x over 2. And then sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So the final answer is going to be -2 inverse cosine of x over 2 plus x square root, x over 2 square root 4 minus x squared plus c. Now, you could have done it a slightly different way. Instead of saying x equals 2 cosine, it could be x equals sine. And that changes the answer a bit. So the other answer that you could have potentially gotten would be positive 2 inverse sine of x over 2 plus x over 2 square root of 4 minus x squared plus c. So this is a possible answer also. With these problems, there's also a domain issue involved in them. Like this original problem, you're only going to be able to integrate it for, so this is the domain, you're only going to be able to integrate it for for values of x between -2 to +2, right? Otherwise, you're getting imaginary. And that also has to make sense here because you can only take inverse sine of values between -1 to +1. Those are only output values of sine. From this, you would also get the same values, the same domain issue. So you just gotta, this is sort of something that has to be taken into consideration. So like I said, this answer right here would have come from the beginning saying x equals 2 sine theta and dx equals cosine theta d theta. And then doing all the work would be slightly different. Okay, let's see. Number 3 is the integral of x squared over the square root of 9 minus x squared dx. If you try to use substitution, it would not work. So we're going to try this trig substitution, bring trig in to make it into something that we can actually integrate and then change it back. Now we're trying to get, this is where the 1's going to go. So your x is for sure going to be 3 something, but it's got to be this one, this first one again. So I'm going to go with cosine. You could go with sine because you could also do cosine squared theta equals 1 minus sine squared theta, and you could put sines in it instead of cosines. That's either way. Dx equals -3 sine theta d theta. So I'm going to rewrite this. So the x squared on the top, that's going to be 9 cosine squared theta. On the bottom, we're going to have the square root of 9 minus 9 cosine squared theta. And then dx gets replaced with -3 sine theta d theta. Now, we can take a square root of 9 out of this. And then 1 minus cosine squared is sine squared. And the square root of sine squared is sine theta. So we're going to get a 3 sine theta on the bottom. So the 3's can cancel, the sine thetas can cancel. And if I rewrite this, there's still negative. It's going to be -9 integral of cosine squared theta d theta. So it's kind of messy, but it cleans up nicely. Now I think I may have made a mistake still. Let's see. Oh, no, I think I'm right. I think I'm just doing it different than the way I did in my work. So in this case here, we would use that double angle identity that we use all the time in parametrics. It's going to be 1/2 plus 1/2 cosine of 2 theta. Right? And so that's going to be -9. And it's going to be 1/2 theta plus 1/4 sine 2 theta plus c. We're going to have to change it back to x. So I'm going to take my relationship here, cosine theta equals x over 3, which is adjacent over hypotenuse. Now I'm going to draw a little picture just to help me organize stuff. So here's theta, adjacent's x, hypotenuse is 3. This is going to be 9 minus x squared. But we do have a double angle in here too. So the double angle for sine we just used on the last one. So this is going to be negative 9 halves theta minus 9 fourths. And it's going to be 2 sine theta cosine theta plus c. Now, theta is just going to be inverse cosine of x over 3. And then sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So the 3's are going to cancel that out. So we're going to get negative 9 halves inverse cosine of x over 3 minus 1 half x square root of 9 minus x squared plus c. Now the other answer you could get, I think, would be positive 9 halves inverse sine of x over 3, and probably the rest of it would be the same. I'll double check if you did it the other way. So yeah, that should be it. So one or the other. The domain here on the original problem is, I mean, first of all, here you can't divide by 0. So actually, x has to be between negative 3 and positive 3, cannot be equal to those, okay? And here, it could be equal to negative 3 and 3, but that's the issue up there. That's the domain issue up there. So that's number 3. Number 4 is the integral of dx over x squared, square root of 16 minus x squared. And the pattern I'm going to try and get a 1 here and minus something squared. So I think we're going to actually use the same one that we used on the last two. Right? I'm going to go with x equals 4 cosine theta. You could do, or you could do x equals 4 sine theta. Either way, dx equals negative 4 sine theta d theta. So I'm going to rewrite this. The top is going to be negative 4 sine theta d theta. The bottom is going to be 16 cosine squared theta, square root of 16 minus 16 cosine squared theta. And this is, we're going to take the square root of 16 out. And then 1 minus cosine squared is sine squared. And the square root of that is going to be sine. So we're going to end up with a 4 sine theta from all this stuff. So that's going to totally reduce that stuff on the top. So what I have now is I have negative 1 over 16. I'll put that up front. D theta over cosine squared theta, right? So how do I integrate that? Well, let's change this to 1 over cosine is secant squared. Oh, I know that one. So that's going to be tangent theta plus c. But we need to figure out what tangent theta is. So cosine theta equals x over 4. That's adjacent over hypotenuse. And I can draw a little picture here to help me organize it. Adjacent over hypotenuse. So this is going to be 16 square 16 minus x squared. So that's going to be negative 1 over 16. opposite over adjacent plus c. So, I mean, we could clean that up. We could say negative square root of 16 minus x squared over 16x. And I think if you did it the other way, you should get the same answer this time. So, okay. Number 4. All right, so number 7 we will do next. So 7 is the integral of x squared minus 9 over x dx. So, this one's actually a little different. So we're trying to get the 1 here. So we want something with trig squared minus 1. Trig squared minus 1. So I think we want to go for that one. So I'm going to put secant in there. So I'm going to say x equals secant theta. You could do tangent instead. The derivative of secant is secant tan. And so if we rewrite this, we're going to get, oh, you know what? We need to put a 3 in here to make that 9. So we're going to get 9 secant squared theta minus 9. And then 3 secant theta tangent theta d theta. And on the bottom, we're going to have 3 secant theta. Now 3's cancel, secant theta's cancel. This is going to be, we're going to take square 9 out. It's going to be secant squared theta minus 1, which is going to be tangent squared theta, which is going to be tangent theta, right? So the top's all going to become that. Now, everything else went away, so we're going to have 3 out front. It's going to be tangent squared theta d theta. Now, we could try and rewrite this as sine squared over cosine squared, but that's not going to help. U substitution won't help. So what we have to do here, and I hinted to this in the notes yesterday, is actually go ahead and use the fact that tangent squared is secant squared minus 1, because we can integrate secant squared. That's just tangent. So we got to use trig identity to rewrite that. So the answer to secant squared is tangent, and then sine 3 theta plus c. Now I need to rewrite this back into terms of x. So I have up here secant theta equals x over 3, which is same as cosine theta equals 3 over x, which might be a little easier. And that's going to be adjacent over hypotenuse. So I'm going to draw a little triangle. And also that means that theta equals inverse cosine of 3 over x for the theta, or you could do theta equals inverse secant of x over 3. So either of those. Here's theta. Adjacent is 3. Hypotenuse is x. This leg has to be x squared minus 9. So when I plug it back in here, I get 3, and tangent's going to be opposite over adjacent. And then I could use this one or the other one. And you could, yeah. So these 3's cancel. And the answer I get doing it this way is the square root of x squared minus 9 minus 3 inverse cosine of 3 over x plus c. Another very close variation is this, but then using that for theta, inverse secant of x over 3, which is a different way of writing the same thing. So there you go. All right, number 9. Now, number 9, I'm going to do it 2 different ways. Okay, so I'm going to do it the inverse trig way, but also number 9 is secretly a problem that we could do U substitution on. So it's not necessary to use this new method on it, but we'll try it both ways. So we'll start with the trig substitution approach. So we're trying to get something 1 minus something trig squared. So That's going to be x equals cosine theta, or x equals sine theta. Dx equals negative sine theta. Now, we got to put a square root of 2 in front, so this is kind of funky, because we want to get that same number, right? So then we rewrite it. X cubed is going to be 2 root 2 cosine cubed. So I cubed the root 2, which give you square root of 8, which is 2 root 2, all over 2 minus 2 cosine squared theta. And then dx is going to be negative root 2 sine theta d theta. So you got to replace dx with that whole thing. Now, this is, we're going to take a root 2 out. It's going to be 1 minus cosine squared. And that's going to be sine squared. And that's going to be sine. So we get a root 2 sine theta here, which cancels out that root 2 sine theta. And so now we have negative 2 root 2 cosine cubed theta d theta. Now, yesterday in the notes, I give you a hint as to how to approach this. So the way to approach this is to break this apart into cosine theta times cosine squared theta, and then use the Pythagorean identity to rewrite that as 1 minus sine squared theta. Seems like we're making it unnecessarily messy, but it's going to work. And then from here, we have negative 2 root 2, and it's going to be the integral of cosine theta minus cosine theta sine squared theta d theta. So we're going to use u substitution here. U equals sine theta, du equals cosine theta d theta. This first one's going to be negative 2 root 2. It's going to be sine theta. So that one's fine on its own. This is going to be plus 2 root 2 if you distribute this. Now it's going to be u squared du. So that's going to be u cubed over 3. So that's going to be sine cubed. Now we still need to change this back to in terms of all of x. So we could let's see, I'll try and squeeze it in here. So cosine theta equals x over root 2, so that's adjacent over hypotenuse. A little triangle, adjacent is x, hypotenuse is root 2, so this is going to be 2 minus x squared. So sine is opposite over hypotenuse. So now if we cube that, we're going to get a 2 minus x squared times the square root of 2 minus x squared over root 2 plus c. So root 2's cancel, root 2's cancel. Final answer, negative 2 square root of 2 minus x squared plus 1/3. You could simplify it like this, or you could just leave it all inside cubed. So that's that answer. If you did it with the other way, you should get the same thing. Now let's see if we can do this problem with u substitution real quick, just to see how that works. It takes a little bit of creativity here. So I'm going to do this one again with just u substitution. So if we make, let's try this out. If we make u equal to what's inside the bottom, 2 minus x squared, so a lot of times what we would do, du equals negative 2x dx, and it doesn't seem great, right? You're like, yeah, but I need x cubed dx. Yeah, but you can have an x, I mean, if we rewrite this, we don't want the negative 2, this would be negative 1/2, and then you would have x squared left, and then du, or the square root of u. Here's the deal. We could solve for x squared. X squared equals 2 minus u. So we could replace that with 2 minus u. And while that seems ugly, we can distribute that division because it's only a one term, right? So, I mean, this is the same thing as negative 1/2, 2 minus u times u to the negative 1/2. So you can use rules of exponents. And you get 2u to the negative 1/2 minus u to the 3/2, u to the positive 1/2. And so now we can integrate, and it's going to be 2. We're going to bump it up 1, divide by the new exponent, minus bump it up 1, divide by the new exponent, multiply by the reciprocal, plus c. One of these 2's cancel there, and that 2 cancels with that. And then we change it back to the original variable. So this is going to be negative 2 square root of u, 2 minus x squared, plus 1/3 2 minus x squared to the 3/2 plus c. And if you compare this to the answer we just got, they are the same. Cool. I mean, that was kind of crazy, but still seems kind of nicer than what we just had to do. Okay. I think we got 2 more problems to go. 11 and 19. So let's see, 11 and 19. So 11 is the integral of dx over x squared, square root of 4x squared minus 9. Now, here's the deal. We probably want to deal with this 4 first, okay? So I'd probably factor the 4 out first. And so square root of 4 would end up being a 1/2. And then you would get x squared minus 9/4. This is kind of something we do like when we do inverse trig and stuff when it's not a 1 right here. Now, if there's any number, so this is where the 1's going to go. So we're trying to get something squared minus 1. So if we go back and look at our notes, that's probably going to be secant squared minus 1. So I'm going to do x equals 3/2 secant theta. And then dx equals 3/2 secant tan theta d theta. So if I rewrite this, it's going to be 1/2. Dx is going to be all that, 3/2 secant theta, tangent theta, d theta. On the bottom, it's going to be 9/4 secant squared theta. And inside, it's going to be 9/4 secant squared theta minus 9/4. So we can take the square root of 9/4 out. And we're going to have secant squared theta minus 1, which is the same as tangent squared, which gives you tangent. So we have a 3/2. So all that boils down to that. Now let's see if we can clean this up. The 3/2 cancel those 3/2. The tangent can cancel with that tangent. We have a secant and a secant squared here, so those can cancel. So what we have left, I think, at this point is the 9/4 and secant theta on the inside. I'm going to move this 9/4 to the front by multiplying by the reciprocals. It's going to be 1/2 times 4/9. And then it's going to be d theta over secant theta, which is going to be 2/9 And secant is 1 over cosine. So really this is just cosine theta d theta. And so this is going to be 2/9 antiderivative of cosine is sine plus c. Got to get it back into terms of the original variable x. So secant theta equals 2x over 3, which means cosine theta equals 3 over 2x. So this could be adjacent over hypotenuse. And we draw a little triangle real quick. Theta, adjacent, hypotenuse. This is going to be 4x squared minus 9. So sine theta equals opposite over hypotenuse plus c. And then we could write it a little nicer and say that it is the square root of 4x squared minus 9 over 9x plus c. Nice. Okay. And for the last problem, 19. So 19's kind of interesting. E to the x, square root of 1 minus e to the 2x. Now, on this problem right here, let's just think what we could do. We could just do regular u substitution. U equals, now if we did 1 minus e to the 2x, that's not going to work. And you don't really have to do this, but we're going to actually try and do the trig thing. I think it might be easier if we replace all the e to the x's with u's. And that just makes everything a little simpler. I think we can get away without it. But that's a little easier to look at. Now we can't integrate this. So we're going to try and make it fit one of those trig patterns. So if we go back, it's going to be 1 minus trig squared. I'm going to go with this first one, cosine. So I'm going to go with cosine theta. So then du equals negative sine theta d theta. And so then we're going to get the integral of 1 minus cosine squared theta. And then we're going to get a negative sine theta d theta. And this is going to be, this is going to give you sine squared theta, and the square root of that's going to be sine theta. And so this is going to be negative sine squared theta d theta. So we got to integrate this. So we're going to do 1/2 minus 1/2 cosine double angle. And then, so the answer here is going to be 1/2 theta minus 1/4 sine 2 theta plus c. So now we gotta, we're going to rewrite this as plus 1/4. So this is going to be 2 sine theta cosine theta is the double angle identity for sine, just so we can figure out what this is. Now up here, cosine theta equals u over 1, so that's adjacent over hypotenuse, and theta equals inverse cosine of u. Draw a little triangle real quick. Adjacent is u, hypotenuse is 1, so this is going to be 1 minus u squared. So theta is inverse cosine of u plus 1/2. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse plus c. We're not done yet because we need to get this back in the terms of x. So this step's pretty easy. We just got to replace the u's with e to the x. So this is going to be plus 1/2 e to the x square root of 1 minus e to the 2x plus c. And that is our final answer. Now, another version of it, if you'd gone with e equals sine theta, you'd get positive 1/2 inverse sine of e to the x, and the rest of it would be the same. So depending on how you attack that problem, that's what you would get. So hopefully you feel like you've had a lot of good practice with this. Let's see, I mean, domain-wise, I was talking about that earlier. Domain, this has to be greater than or equal to 0. And here also, e to the x has to be between -1 and +1. Otherwise, you can't take inverse sine of that. And so, I don't know, I don't know if we take natural log on both sides. E to the 2x is less than or equal to 1. Take natural log both sides. We get x is less than or equal to 0. So as long as x is less than 0, we're good, which I think makes sense because if x equals 0, e to 0 is 1. So that's that boundary case. If x is bigger, then this is going to be bigger. This is going to become negative. So the domain of this problem is that x has to be less than or equal to 0. And the domain for the last problem, the inside of this has to be 4x squared minus 9 has to be greater than or equal to 0. So usually on these problems we do line checks because it's, the last one we got away without it. So we say, okay, well, x equals 3/2, x equals -3/2. And these ones can't be equal to 0 because it's division by 0. So if and x cannot be 0 itself either because that's in the denominator. So these would be open dots, -3/2, +3/2, test a value, x equals 2, positive, true, false, true. So this is the domain for this one. And that also gets rid of the whole 0 thing. So the domain for this one is -∞ to -3/2, and 3/2 to +∞. We could check this. So we need this number to always be bigger than 9. And so if you plug in 3/2, that's 9/4 times 9, that's 9. And then so anything bigger than it, positive or negative, because the negatives get squared. And then x can't be 0 either. So that makes sense for that domain. I don't know if there are any others that I didn't do the domain for. I mean, I did on the first couple. So the domain of this one is the inside x squared minus 9 has to be greater than or equal to 0. Also, x cannot equal 0. So x plus 3, x minus 3. The easiest way to do these is a line check. So you guys do some weird things. So it's going to be solid dot -3, solid dot at 3, test the value, x equals 4, positive, true, false, true. So the domain, this is number 7, is -∞ to -3, union 3 to +∞. And brackets, I think we can use those values. So that was problem 7. Problem 4, x cannot be 0, and 16 minus x squared has to be greater than or equal to 0. So it's going to be 4 minus x. In fact, it can be equal to 0 because it's in the denominator. 4 minus x, 4 plus x. So x equals 4 and -4. We do a quick line check. These are open dots. Test the value. X equals 5 is false, true, false. So this is your domain, but 0 can't be in it. So I guess we'd say -4 to 0, and then 0 to 4 would be the domain for problem 4. So it's kind of interesting. All right, that's it. These are kind of tedious problems, but that was some good practice.